Welcome guys. So in this video, let's talk about homomorphism. Okay, so now after previous that we already have the quotient group idea, right? So talking about homomorphism should be a good starting point. Okay, so hope you guys subscribe to my channel. Okay, so before I start, I want to talk about give a notation of S3. So symmetric group of permutations 3 order. So let's phi to be x1 mapped to x2, x2 mapped to x3, also x2 mapped to x1, and x3 mapped to x3. And then let's define psi to be x1, x2, x2 to x3, x3 to x1. Okay, so you can view S3 as a permutation of the geometry of triangle. So psi is just rotation 120 degree, and the phi would be let's say this is 1, 2, 3, right? So phi would be fixed x3, so you can this and flip this. Yeah, so this is phi, this is psi. Okay. So a simple check is that if you're working and psi at x on phi, tell the x1 change to x3, x2, x2, x3, x1. And also psi phi will be x1, x1, x2, x3, x3, x2. Okay. And also if you use psi squared, so psi squared just rotation 240 degree, right? So x1 to x3, x2, x1, x3, x2. Okay. And the final is a psi inverse phi. So it's x1, x3, x2, x2, x3, x1. Okay, so collection of all these 6 will form a group. Okay, so operation formula is that the phi x on psi will be psi inverse x on phi. So this is the non-abelian group. Okay, so just a notation. Yeah, so with this notation, we can talk about some examples. Okay, so this video will be the first, we will prove the homomorphism, the first isomorphism theorem. So I already proved first isomorphism in my other videos, but I will prove it again. Okay, so definition. So if you have a group G phi map phi to G bar, it's called group homomorphism. So this idea is so important that yeah, I mean probably the most important. If phi of xy, so basically you respect the group's object, the group operation, right? So phi of xy should be viewed as a phi of x, phi of y. Okay. Okay, so simple example. So simple first is that the identity must map to identity, right? Identity in G must be mapped to identity in G bar. And the proof is basically because phi x identity will be phi of x. So be phi of x in a phi of identity, right? So you can, in a group, G bar is also a group. So you can delete phi of x. So you get the phi of e must be 1, right? So must be identity. Okay, so I mapped identity to identity. Okay, so yeah, let's talk about another example. Let's see. So example, there are lots, so many examples. So let's say we take a group to be the real number on the addition. Okay. Okay, and the G bar to be the non-zero let's see, G bar to be a non-zero real numbers with the product being order and multiplication. So G bar, let's say G bar is a basically it's the non-zero element and in the multiplication. Okay, so simple. So we can map. Let's say we can map a to the. If you have a real numbers, let's map it into 2 to a. Okay, so this is homomorphism because 5a plus b will be 2 to a plus b, will exactly be 2 to a, 2 to a b. Okay. Yeah, there are lots. There's still a lot. Okay, so right. I mean, yeah, there also if you have the group G to be the integer with the addition, and then you pick up n, you pick up in integer, and then you can map G bar into basically z modulo and z in addition. So map just map any integer to modulo n. So map x to x mod n. Okay, so also homomorphism. Okay, and also if you take G to be all the real numbers, let's say positive real numbers in the multiplication, and you can define G bar to be all the real numbers on the addition. So you can use the log, right? So you can define 5x to be log 10x. So easy to show that 5xy will be log 10. So this x plus in this products, right? So will be this. Or it can be separate into two. So this is 5x, 5y. Okay. So these are all examples. Okay. The most important, one important example is that you take all the group to be all matrix. Okay, I should say all the invertible matrix. So your group will be general linear group with any field coefficient, and you can take homomorphism to G map to the real numbers. So the real number yes would be real non-zero real number. So that so G bar should be a non-zero real numbers in the multiplication, and you map each element G you map each element G to the determinant of G. Okay, so easy to show that the determinant of AB, right, is the same as determinant A, determinant B. So this is phi AB. So you can map the matrix to you can map any matrix to its determinant, and it's exactly the homomorphism. Let me just clean. Okay. Let me just write careful. You know, I mean, to write mathematics is hard, right? So I'll write everything. Write everything correctly is difficult. Okay, especially for the first time. Okay, so let's see. Okay, so we already say that. So let's say we have a canonical example. So canonical example is that I already say if n is a normal subgroup of G, then I can construct G quotient n, right? So there is a surjective map from G to G quotient n, and then let's do phi. So just map to element G into the representative in the G quotient n. Okay, so obviously that this is the homomorphism. Okay, so the proof is trivial. Okay. Let's say yeah. So I believe that yeah. So a representative will basically Gn. Okay. So why this is trivial? Let's say so if we have a x y, and in here in this and you map it basically this is x y n, right? And then you map into x n y n, right? This is 5x 5y. Right, so but you know that the yn is the same as y, right? So you get xyn squared, which is xy n. Right, so proof is proof is done, right? Okay, that's talking about the kernel. Okay, so if you have a definition, if you have a group G to G bar, the kernel phi means that 5x such x basically all the x such maps to identity cokernel. Also the cokernel. So cokernel means that the G bar quotient the image of this phi. Okay, so simple exercise. So for you guys to check is that the kernel will be a normal subgroup of G, and the image image will be a subgroup of G bar. Is correct. Let's see. So kernel must be a normal subgroup. This is trivial. Okay, but the kernel is a normal subgroup. Okay, so let's maybe prove this. Okay, so kernel means that all the map to identity, right? So we need to prove it's a normal subgroup. Okay, so how to prove it, right? So we need to prove that x you map x kernel phi will be the same as kernel phi x. Okay, let's see. But notice what? So notice that the 5x inverse will be 5x inverse, right? So inverse will commute with 5x because this is homomorphism. So this is due to that if you get 5x x inverse, you get 5 identity, which is identity the same as 5x inverse, right? Inverse. So if you tell you that the 5x inverse will be 5x inverse. Okay, so once you have this, right? Let's see. Okay, so once you need to check this, but the no, okay, so notice that if you get gk, so let's say we take this element to be k, call it k, right? We take any element called gk, g inverse, where g is in the group g, will be, let's say we ask that so we need to check that this guy is still in the kernel, right? If it's still in the kernel, that we are done. So we need to check this is 0, right? But this is stupid because 5g equals to 5k equals 5g inverse, and then this is 5 identity, right? This is identity because it's kernel, so you get 5g inverse, and then by the homomorphism property, you get g inverse, which is 5e, which is e, right? So this shows that the kernel is a normal subgroup. Okay, so easy to check that image phi will be let's see. Yeah. Yeah, so image phi should be must be a normal subgroup. This can be easy checked. Yeah. Yeah, so this is called cokernel. Just map G bar quotient image phi. Okay, so it looks like that it looks like the cokernel. Yeah, okay, so we need to somehow we need to check that where this is normal subgroup. Yeah, but I remember that it's just a subgroup. Yeah, so I will check it after. Okay, so if your phi is isomorphism, so it means that it's a bijective and the homomorphism. So if you can construct G to G star such that phi is isomorphism, then we are abstractly to say that G is isomorphic to G star. Okay, so this is equivalent relation. So basically, if they we say that these two groups are isomorphism, means that abstractly they are the same group. Okay, so they are the same group abstractly. Okay. Yeah. So okay, so let's prove the first isomorphism theorem. This should be okay. So if you get G to G bar, which is a homomorphism, then the you have kernel, right? So let's say you have this kernel is K. Kernel is a normal subgroup of G, right? Then and then it's onto. So let's say this is onto. Then you can prove that the G bar is isomorphic to G quotient K. Or basically, if you neglect onto, then you have this, then you are just saying that the image phi is isomorphic to G quotient the kernel phi. So this is the first isomorphism theorem. First iso theorem in a group. Yeah, so there are 3 isomorphism theorems. This is the trivial one. The first simple one. Okay, so proof. Okay, so we need to establish this map, right? So we need to establish G bar equals to so now since I only say in the original theorem this is image, right? But so I can replace this to be surjective. So I can just prove that the G bar isomorphic to G quotient kernel phi if I replace this to be surjective, because I already know that image phi must be a subgroup, right? So I can reduce the case to this map to be surjective. So I only need to prove that G is isomorphic to kernel phi. Okay. Okay, so that means we need to construct a psi map to G quotient kernel phi, kernel phi to the G bar, right? And the previous isomorphism. Okay, so how to do this, right? So each element in this, as this is k, right? So this is xk. This is element that I just map to what 5x. Okay, so simple. So now we need to show that this is surjective. And okay, so first, we need to prove that is homomorphism, right? Homomorphism. So this is trivial because psi of xk yk, right? By definition, is phi of so this can be rewritten as xyk squared, so xyk. By definition, it's phi of xy, right? So, but phi of xy is homomorphism, right? So this is basically phi of x, phi of y. Oh, and then you can write this psi of xk, psi of yk. Okay, so this is the homomorphism. Okay, and the second, we need to show that it's surjective. Okay, but this is trivial, right? Because original map is surjective, right? So replace in phi of x is always surjective because you can just xk map to phi of x, right? So surjective is trivial because my assumption is that this map is surjective. Okay, so that's calling about injective. So injective means that the xk yk, right? If so we need to show that if xk how should I say it? So injective means that if phi of x equals to phi of y, then x must be the same as y, right? Okay. So phi of x means phi of y, let's say. So we means that, well, what? Means that phi of xy inverse is what identity, right? So xy inverse belongs to k, right? Because k is kernel phi. But what? But this shows that xk equals to yk. Okay, so which is the same as so these two are the same in the left, right? So that means x equals to y in a G marker K. Okay, so we prove it's injective, homomorphism, surjective, right? So this map is isomorphism. Okay, and there is a subtlety that you should first prove that this is well defined. Yeah, so I leave exercise for you guys. Yeah, it should be trivial. Okay, so after this, we already proved that the first isomorphism theorem, right? So in the next video, we can talk about the applications and talking about the second and the third isomorphism theorem. See you guys next videos.